Section 6.2, Exponential Functions and their derivatives. To begin, let's review some basic concepts about exponential functions. So to begin, an exponential function is one where the variable is in the exponents place, such as g of x equals 2 raised to the x power. And we also have to recall some laws of exponents. First one is if we have the same base, we can go ahead and add their exponents. Second, if we have the same base and we're subtracting the exponents, we can write it as a fraction and vice versa. If I have an exponent raised to another exponent, the exponents may be multiplied. And if I have an exponent applied in the parentheses, it applies to everything in the parentheses separately. And we also have exponential functions and their graphs. Their graphs they kind of look like an L, and the figure that this graph makes depends on our base. So if our base is a number, a fraction between 0 and 1, it looks more like an L shape, where as x gets bigger, it's getting closer and closer to 0, but not quite. And as x gets bigger but smaller, then we see our graph continues to get higher and higher up, thus going to infinity. And if our base is anything bigger than 1, then we see that it reflects over the y-axis. Now with these figures, we can also attach some limit definitions. If b is greater than 1, which is this graph C, so look at your graph C, then we see as x is approaching infinity, our limit would be infinity, and as x is approaching negative infinity, then it would approach 0. So we see that if it gets larger, as x approaches infinity, our x numbers are getting bigger and bigger and bigger to infinity. Our graph is reaching infinity. And as our x values are getting smaller, so approaching negative infinity, it's getting closer to 0, but not quite. And that second piece, you can look at your graph A for this. If b is between 0 and 1, the limit as x approaching infinity of b to the x power equals 0, and the limit as x approaching negative infinity of b to the x equals infinity. So a quick graph. To find the limit of x approaching infinity of 2 raised to negative x power minus 1, and sketch its function. Alright, to begin, let me just quickly rewrite this because we have a negative exponent. That would be the same as if I want to make, 2 raised to negative 1 times x. If I want to make that negative exponent positive, we write it as 1 over 2 to the x, right? So the same as 1 over 2 raised to the x power minus 1. We can then apply the limit to each term. So we have the limit as x approaching infinity of 1 over 2 to the x power minus the limit as x approaching infinity of 1. Now for the constant, that second term is just the constant, so it's just 1. Now for our first part, the limit as x approaching infinity of 1 over 2 to the x power, well, that would be where we see our graph is approaching 0. Think of this first one. Our base, our b, is a fraction between 0 and 1. So as x is getting bigger, as x is approaching infinity, it's getting closer and closer and closer to our x-axis, so 0. So we have 0 for that one. So for our first one, you get 0. For our second one, it's just 1. 0 minus 1 is 1. Derivatives of exponential functions. So our derivative of our e, our natural exponent function, Our derivative is just e itself. So special note, while the derivative of a natural exponent function is itself, when the exponent is something other than x, the result isn't as straightforward, as we'll see in our next example. So in this next example, differentiate the function y equals e raised to the tangent of x, and we have this little helpful hint. So when we're working with our exponent, we have to take a moment to take the derivative of our exponent. So here we see d of dx of e raised to the u power is the same as eu times du dx. So we take our function u and you take your derivative in terms of x. That's what that means. All right, so we have to label our exponent as u. All right, so our exponent is right here, tangent of x. U is equal to tangent of x. Now let's go ahead and take a derivative. Take our derivative, but let's rewrite it as u, just like our notation has. So that we have d dx of e to the u. Well, we're told our answer is e u times du dx. What is du dx? That's our derivative, our function u in terms of x. Now our derivative of tangent of x, you have to recall your rules of trigonometric derivatives. So the derivative of tangent is secant squared. Again, it's just a definition. So let's make those replacements. Our u, what is u? U is tangent of x. So we have e raised to the tangent of x times du dx. What is du dx? It's secant squared. And that is our answer. So I left a little part here as a special note. Write in your own words, what are the steps for finding the derivative with e? So pause the video, think about it, write it in your own words, and then continue the video. Moving forward. Example, find y prime if y equals e raised to negative 4x power times sine of 5x. Okay, so we see we have two arguments of x being multiplied, right? We have our e raised to negative 4th power and our sine of 5x, and they're being multiplied. So because of this, we have to follow our product rule. Product rule. And just a brief reminder, your product rule is if you label the first one f and the second one g, it's f prime times g plus f times g prime. Okay, let's go ahead and set it up. Now I'm going to set it up without actually finding the derivative. I'm just going to write prime and take the derivative in the next step. So that I have f prime, so that's that e to the negative 4th power. So e to negative 4th power x. I need to take the derivative of that. I'll come back to that. Times the second part, sine of 5x. Okay. Plus f, which is e raised to the negative exponent of 4x, times our second part, and I need to take the derivative of that. So we'll do that in my next step. I'll just write a prime to remember I need to take the derivative. Okay, let's go ahead and take those derivatives. So for the first one, the derivative of anything with e is itself. So we first have e raised to negative 4x times the derivative of the exponent. So what's the derivative of negative 4x? That would just be negative 4, right? That's our first part. That second one, we just bring it down. It's the same thing. Sine of 5x. Plus, the first one is just itself. We just rewrite it. And then here we actually have chain rule, right? So let's take the derivative of the outside. The derivative of sine is negative cosine. So I have negative cosine of 5x. And then I have to take derivative of the inside, which is just 5. I made a mistake. The derivative of sine is not negative cosine. It's just cosine. Okay, let's clean this up. So we can bring the negative forward. So I have negative 4e raised to negative 4x power times sine of 5x plus e to negative 4x times 5 cosine of 5x. Now, something we can do is factor out that e to negative 4x power that each one of these has. So that we have e raised to negative 4x times everything else. So negative 4 sine of 5x plus 5 cosine of 5x. And an extra step you can do, just in case maybe your answer doesn't match the one in the back of the book, is we do not like to begin with a negative. So you can always swap your two terms. So we have e to negative 4x power times 5 cosine 5x minus 4 sine of 5x. And there we have it. We took the derivative, and in this problem, we worked with a natural exponent. We had to work with product rule, and within our product rule, when taking the derivative, we had to use chain rule. So this problem really uses everything you've learned in your past Calculus 1 course and highlights it in one single problem. All right, moving forward. Properties of natural exponential functions. The exponential function f of x equals e to the x is an increasing continuous function with domain R and range from 0 to infinity. Thus, e to the x, when it's greater than 0 for all x, also follows your same limit rules as your exponential functions. So the limit as x approaching infinity of e to the x equals 0, and the limit as x approaching positive infinity of e to the x equals infinity. So you have your graph for e. It's something like this, right? So as x is approaching negative infinity, you see it's approaching 0. And as x is approaching positive infinity, it just keeps shooting up, going higher up. And as usual, your x-axis is your horizontal asymptote. And if you add any constant k, it just moves your horizontal asymptote up or down, whatever k units it may be. All right, let's do an example. Find the limit as x approaching infinity of e raised to the 2x power divided by e raised to the 2x power plus 1. All right, we're going to use a helpful tool we learned in Calculus 1. We're applying the limit as x approaching infinity. We can divide by our largest exponent of our denominator. So that we have e raised to the 2x divided by e raised to the 2x. And we're just doing that for each term. E raised to the 2x divided by e raised to the 2x plus 1 divided by e raised to the 2x. All right, so that we just get 1. divided by 1 plus, and then because we have that 2x in the denominator, we can write it as a negative exponent. So e raised to the negative 2x. Alrighty, now we can go ahead and apply the limit to that one term. So that we have 1 over 1 plus the limit as x is approaching infinity of e raised to the negative 2x. And according to our definition, we said as e is approaching, as we have e to some exponent x, it's going to give us infinity. So our answer is going to be 1 over 1 plus 0. Now the reason it's 0 is because, let's make a replacement. Let's t equal negative 2x approaching negative infinity as x is approaching infinity. So the limit as x is approaching infinity of e to the negative 2x is equal to the limit as x is approaching negative infinity of e to the t equals 0. So our answer for this problem is just 1 over 1, which is 1. Last piece, integration. Now integration with e is nothing new. You're just going to follow all of your integration steps that you have learned in the past. So to begin, our derivative of e to the x is e to the x. So now that we're talking about integration, our integral for e to the x is just e to the x. Pretty simple, right? It's just itself. So let's do an example. Evaluate the indefinite integral x squared times e raised to the x cubed. I forgot to write dx. All right. Now this type of problem, it would be helpful to use U-Substitution, or the substitution method of integration. Now the reason we would like to is because we see a function and we can see a sense of their derivative within the function. So let's go ahead and use that U-Substitution. So if we let u equal x cubed, we go ahead and take the derivative. Du dx equals 3x squared. Now this is just a helpful tool. It's not real. You can't treat it as a function, but you can, as a fraction, but you can think of it as times dx times dx. So you can write it as a partial derivative. You can just write it this way. You don't have to think of it as the way above. All right, so we have these two important pieces that we're going to use for our U-Substitution. All right. So that we have, I'm going to rewrite it, e raised to the x cubed times x squared dx. So we see here that we have the x squared dx, but we need to incorporate a 3. A 3 is missing. Well, we can go ahead and multiply by 1, a special one. So we're going to use 1 over 3 times 3. That's still 1. We're not changing the value of it. So I can write a 3 and a 1/3 because they're being multiplied, right? So we're not changing the value, it's 1. So we have this part right here, which is our du, and this part right here, which is our u. So let's go ahead and make that replacement. So that we have 1/3 e to the u du. Let's go ahead and take the integral, the antiderivative, so we're left with 1/3 e to the u plus c. Let's go ahead and make that u replacement. So then we're left with 1/3 e raised to the u power. U was just x cubed. And there we have it. That was the integral. Now, as you may see, it kind of is a bit, well, when you see the problem from the very beginning, let me zoom in. You kind of see what should happen. You know that when you take the derivative, when you're taking the derivative of e, you take the derivative of the exponent separately. So you kind of see how that derivative is within our function. But you know that there's something to work in, considering that the derivative of x cubed is 3x squared. So you know that 3 was missing. So if you were caught on that from the beginning, you could have just written that 1/3 to compensate for that. All right, so this was working with e, taking the derivative, working with integrals, and a quick review on exponential functions. This was 6.2, exponential functions and their derivatives. Thanks.